Hello and welcome everyone. It's my pleasure to introduce our KITE Research Round speaker of today, Dr. Konrad Körding. Dr. Körding runs his lab at UPenn. He is interested in the question of how the brain solves the credit assignment problem and similarly how we should assign credit in the real world through causality. In extension of this main thrust, he's interested in applications of causality in biomedical research. Dr. Körding has trained as student at ETH Zurich with Peter Koenig, as postdoc at UCL London with Daniel Wolpert, and at MIT with Josh Tenenbaum. After a decade at Northwestern University, he's now a PIK professor at UPenn. Just a note that you're watching this live on YouTube. To ask questions, please use the Slido link that was provided in the invitation link. And now please join me in welcoming Dr. Körding. And I pass the mic.
Great, thank you so much for the great introduction. Today I will talk about the pitfalls in health research when we apply data science methods, or more specifically, when we apply methods that are aimed at making machine learning predictions. Now, I'll be talking about machine learning. I will not be talking about causality today. Causality is a different topic, but today I rather want to talk about the many ways how we can do machine learning in the wrong way. But let's first do some introductions here. So what's the outline? I will first briefly review what machine learning is useful for, why we use it, how it's useful, and what it brings to the table. And then I will talk about the generic settings that we have in machine learning, in diagnostics and typical uses, and then I will talk about a number of ways of doing it wrong. Because I think in a field where machine learning is relatively new, and I think in most areas of medicine, machine learning is relatively new, there are mistakes that people make. And unfortunately, in most areas where people start using machine learning, they make the same mistakes early on. And so let's talk a little bit about the mistakes that are there. But first, like some introduction, why is this important? So this is a fun analysis we did where we plotted as the function of the year, using simple Google searches, the number of publications and patents that use machine learning together with biomedical. And what we see is we see an almost exponential growth over time. It of course means that sometimes in 30 years, all papers will be using machine learning, which is a little bit worrying. But in a lot of scenarios, machine learning is just a really useful tool that we use to, in an engineering way, solve small problems. So what are we using machine learning for? So sometimes machine learning itself is the target. For example, we might want to use mobile phone data to estimate what the mood is for us in the day, because we want to tell you a history of what your mood was across time, because maybe you can learn something from that. Keep in mind, this is not to solve the causal problem. This is not by itself to tell you, well, running is going to make you feel better or something. I mean, this is just a way of pre-processing the data, which is basically figure out how over time we feel. There are other cases where we use machine learning to understand data. That often, for example, is an issue in brain science. I want to understand what's the information that is shared between what I see outside there with what's happening within my brain. And we can then use machine learning to estimate things like mutual information, or like which of the information in the outside world is represented in the brain. What does our brain tell us about the outside world? There's also a third scenario that I think is quite interesting, which is machine learning provides a benchmark. In neuroscience, us humans always make models. And the same thing is true, say, in rehabilitation research, where we're like, yeah, we look at the data and we think that this is what gives rise to that. So therefore, we think this is a good model. And it's often based on a lot of human knowledge, which is, of course, great if that human knowledge is good and correct. It's, of course, much less great if the human knowledge that goes into this is wrong. And if we are honest, for a lot of things like brains, we might not always be right about the assumptions that we have there. Now, what can machine learning do here? You could say, I take the data that I have, and I say, I can have a human produce a model based on the data that I have, or alternatively, I can take the data that I have, put it into a machine learning model. That machine learning model will generally do better than the models that we build as humans, unless this would be a real exception that our model is actually better than what machine learning does. But in doing so, machine learning gives us a scale. The model that we just built, does it describe 1% of the variance of what the machine learning system does? In which case, there's something big that we're missing when we construct that model as ourselves, or does the human-made model describe almost all of the variance? So in that sense, I propose that whenever we build models, we should also run machine learning to get an idea on how good we could be in that domain. Machine learning is also often seen as a model of the brain, where we could say, what would be, like the problem that the brain solves is often a similar problem to the problem that a machine learning system solves, which is, if you want, make good predictions in real world scenarios. Now, that's not everything that the brain does, but it's certainly one of the things that the brain does, which is predict what's happening. And in that sense, you can say it wouldn't be very surprising if the brain shared certain properties with machine learning systems. So there you saw three very different uses of machine learning. And now one more thing that we often want to do with machine learning, in particular as it comes to health, is use it towards diagnostics. And there's arguably two ways how we can approach diagnostics. The first thing is we can measure the right thing. What does that mean? We could, if we want to know if someone has COVID, we can try and identify antibodies to COVID or look for the viral RNA, things like that. And that's a great way of testing things. It's not a very scalable or efficient way of testing for things, no, because we need to run molecular biology on every single sample. The alternative in the realm of diagnostics is you just measure lots of stuff. Maybe the queries that you put into Google and where you are and how you use media and the way you move, the accelerations in everyday life, and hope that if we combine all of these things together, we get good estimates. You can see the advantage of the first approach is that it really gets you at truth very directly. The advantage of the second thing is that it's very, very scalable, that we could basically build that at crazy size. So I will now review the standard workflow that people use for machine learning. I know it will be well known for a lot of you, but I just want to make sure that everyone is on board as we start speaking about these topics. So what's the workflow? The first thing is we produce data where we know what the correct diagnostics is. We find out if people actually have the flu. We find out if they're able to move in a certain way. We find out if they have Parkinson's disease, all those things. And then we train the machine learning system based on all kinds of data that we have about the people. And then we test if our machine learning system really works. And then if we are successful at that, we can use it to make cheaper, better diagnostics. And this kind of pipeline is used in lots of different ways. So let's look at the way how this really works, because it turns out that the typical supervised machine learning people use in that domain always takes on the same properties. So what we have is we have what we call label here, which is for each sample, we know what the label is. This person had Parkinson's disease, coded as 1. This person did not have Parkinson's disease, coded at 0. Or this person can get took 12 seconds on a timed up and go task, and that other person took 5 seconds on a timed up and go task, and so on and so forth. So in each row here, it could be a person, it could be a cell, it could be an image. But the important thing is for each of them, we will have a label which tells us what the right thing is. And then we have features. That could be, I know how far you walked yesterday. I know how many miles a day you drive on average. I know how often you looked for the word scared. So what we do is we in the standard supervised setting is we just have a matrix features by samples and then a label where for each sample we have what the ground truth is. And then we test and it gives, we train and it gives us a model. And then what we do is we take the model with new data for which we have the features and we make predictions. This is how it looks like when we apply it, when we just want to test it. We also will, for the same people, get what the truth is, and then compare the predictions to the truth to know how good our machine learning system is working. Typical example, we take a questionnaire that deals with mood, PHQ-9, and we want to detect it from mobile phone sensors. We've been together with David Moore, we've been doing a lot of analysis where we basically get all kinds of data from phones and we install software on phones that basically spies on the volunteers of that in every imaginable way. And we get all the sensor readings of it. And the question is, how good can we at knowing how they feel when they then fill out a PHQ-9 afterwards? So what are the sensors? We have accelerometer, we have magnetometer, we have barometer, we have brightness sensors, we have like a GPS, the screen, the keyboard, and the microphone, and so on and so forth. So in more recently, we're interested in, say, the text that people type on their phones. So let's see a bit how that looks like. So here, for example, and this is work with the Gyroman lab, I should say, where we have how long every day people use their phone. What we see here is as a function of the time of the day, we have episodes of phone use, and then we have daily use in seconds of that. And we could say that how long I use my phone could very well be indicative about how I feel. You know, like maybe I call people when I'm good, or maybe I call people when I'm not good. Machine learning will ultimately help us figure that out. We will have GPS data. Here's from a volunteer, where in Chicago they spend how much time. Why could that be relevant? Well, it could be that on days where you feel good, you go to the gym, and on days where you don't feel good, you don't go to the gym. And in that sense, GPS data could be indicative about how you feel. And of course, now GPS is basically producing a movement pattern through two-dimensional space where we can see where you've been over time. So how should we analyze the data? Well, we can extract feature from GPS. We can say location variance. If you feel better, you might be in a larger space. Or it could be that if you feel better, you could visit more spaces. There could be more clusters. Or there could be something about the entropy of the space. Or it could be that if you feel good, you spend less time at home. Or it could be that if you feel good, you will be more active during the day and less active at night. Or there could be something about the transition time, how long it takes you to get from one place to another. Now, which of these do you think correlates with the PHQ-9? Well, all of them. Okay, so here you see the various features. We found a single feature that's not correlated, only two features that are not, three features that are not significantly correlated. We split the questionnaire responses between PHQ smaller than 5 or greater or equal than 5, and lo and behold, they almost all are significantly different. Okay, that's good news. It means we can know something about how people feel based on that. And now we can combine them in some trivial machine learning, where we can say the probability of having depressive symptoms is a linear combination, or it's like a nonlinear function applied to a linear combination of various features that we have for them. And because it's machine learning, we will use regularization. So we will try and fit that whole thing with a B vector that has that has small norm. No, it's like the standard approach that people would have. Now, what do we have here? So the accuracy is like better than chance, of course. Usage duration, usage frequency, all features. Yeah, we get better if we use more features. And we have like some amount of specificity and some amount of sensitivity. This is just for distinguishing the depressive mood, yes versus no. So this is great because it's significant. This is not great because it's totally useless. Let me highlight that. Now, like the sensitivity and specificity that we get out of all those phone features, mind you, text is not in it, and it could be that it's very different for text. It's all significant, but if the system tells me today, I'm like 70% sure that someone feels bad versus today, I'm just 25% sure about it, that will not be enough to drive any meaningful intervention. And of course, we tried more complex machine learning. Now, there are certain things that we can do really quite well. We can use machine learning to detect semantic location. In fact, we can do that better than Foursquare, where we take all the data that we have and we ask, can we know that someone is in a travel situation? Are they in a nightlife spot? Are they in a spiritual spot? Are they doing outdoors and recreations, and so on and so forth? So we are very good at solving those kinds of tasks, like what is the place where you are? What are you doing where you are? But we're quite bad at knowing if you're depressed or non-depressed of that. Why? If you look at all these features, they're very highly overlapping. You know, like with a slight effect. Oh, wow, we have an alarm going off here. I apologize for that. It has a very slight effect that non-depressed people spend more time at work, and depressed people spend more time at a professional or medical office. But again, if you look at the distributions, they're very overlapping. And that explains why we aren't good at knowing if someone is actually depressed or non-depressed. So we can basically learn an awful lot of true information about the relationship here, but it's very hard to produce results that are like really medically actionable. And but let's talk a little bit about how to do good machine learning. So if you get into machine learning, it is a truly bewildering field. You know, like you read about support vector machines and support vector regression. You read about k-nearest neighbor methods, about XGBoost, which is a random forest method. You use about generalized linear models. You learn about stacking. And people, when they get into machine learning, often believe that becoming good at machine learning is mastering and understanding all these techniques. I'm not sure to which level that is true anymore, and you can learn about all those techniques in machine learning courses. But I think there's a better way for most people to do it, which is use automatic machine learning instead. So what does that mean? There are lots of people build machine learning techniques, and there are, say, 20 techniques that are reasonably popular. What's a good way of dealing with that? Well, I can have a PhD student who, like, for some reason understands which of these 20 techniques is best. Turns out they will often be wrong. I can alternatively ask a PhD student to implement a whole bunch of them and choose the best one. But then the problem is I still have this, I will start reusing data and they will become creative. And by doing so, they will give us false positive results. So the radical alternative is what's called automatic machine learning. How does it work? It implements every single one of these machine learning techniques that we just spoke about. It implements all these 6 and many more of them. In fact, it implements them for many different parameter settings. And then what would you do with it? Well, you would be like, well, look, like random forests are really good. And support vector machines are kind of good. And like the linear techniques are really, really bad. And you would be like, yeah, therefore, I think I want to use this one, but I'm not sure if I should use both of them. So what automatic machine learning does is it uses all of them and then uses machine learning to combine all the different machine learning techniques. Why is this so cool? It no longer requires humans to do the task of doing this kind of machine learning. It all does it automatically for you. So you don't need to worry which one is the right technique. It runs all of them. And at least in our hands, automatic machine learning does surprisingly well. And what's our general finding? Auto-ML, and we tend to use Auto-sklearn, which is from Freiburg University, is usually better than published results when we reanalyze published results that's there. It is usually better than our own results. I mean, like, yes, we can beat automatic machine learning if we really put effort into this. But that is a lot of effort for a team that is very good at machine learning already. And it's very, very easy to apply. It's just a few lines of code. So here's some interesting comparison of techniques, but let me talk about some of our own. So this is from a sequence of 2 papers that we wrote with the Isidore paper, where they went through liquid biopsies papers. And I should say, we've been using automatic machine learning for all kinds of problems where they seem to be working very well. Here we reanalyze data from the liquid biopsies field. So what does liquid biopsies mean? It's this emerging field where they take a small amount of blood or some other bodily function, they get at a bodily substance, they get about the concentration of all kinds of chemicals in there. And then for each sample, they have basically the concentration of what, like a dozen or few dozen of them. And they then want to predict if you have some disease based on that. And on the left-hand side here, you see the comparison where on the x-axis, you have what the literature reported is the area under the curve. Keep in mind, for people who haven't heard about the area of under the curve, you have to usually set a threshold and you call it, say, disease above the threshold, you call it non-disease below the threshold. But where you set the threshold, you can always set the threshold so that you trade off. You either have more false positives and then you have fewer false negatives and vice versa. AUC is a measure of how good a classification system is that is basically just the integral of that. It basically measures how much information do you gain about the disease state in this case. And now what you can see here is the AUC that the literature reports tends to be considerably worse than the one that automatic machine learning reports. But automatic machine learning has an extra advantage. So if lots of people use the same machine learning systems, the machine learning systems can learn something about the kind of data. You could, for example, have, when we deal with liquid biopsies, support vector machines are always bad. Now, I'm just making this up as an example, in which case we would sometimes statistically make the mistake that we use support vector machines because our data set is too small. So there is a version that you can see on the right, on the lower right-hand side here, where what we do is we have, every time we learn, we have a new data set, a new liquid biopsy data set. We not only solve that problem, but we also try and make things better for all other liquid biopsy techniques by basically producing a table of which techniques are how attractive and which parameter settings are how attractive. So if we do this, this only uses knowledge about the domain of liquid biopsies. It doesn't use information about this specific measurement. It just uses generic information about the nature of noise and the nature of data in the relevant domain. But what you can see is you get a couple of percent points better than if you just use naive automatic machine learning. On the left-hand side, you see that automatic machine learning is usually better than humans, than what the literature does. On the right-hand says, and it gets even better if more people use the same machine learning pipelines. And so we really see that, we really believe that the switch to more automatic machine learning and to more sharing such pipelines between labs can promises to basically make machine learning better in the domains. So let's go through a related example of machine learning in neuroscience, because my lab has been working a lot on it. It's the kind of data that our collaborators Miller and the Bensmeyer lab use. So you have electrodes in a brain. You want to figure out what the brain wants to do. That's the decoding stage. You then control a robot arm, and then there's an encoding stage where it's, if I want to give back to the brain what would have happened had the brain really felt the hand, with an encoding, what would the brain do if that was the input to the brain? And what we have coded here is the equivalent of automatic machine learning. My lab has slightly adapted it to the task of machine learning in neuroscience, but the same techniques work in a lot of domains. And you see the methods that the field of muses, Wiener filters, Wiener cascade Kalman filters do make considerably larger, think twice as much of an error in this case as these ensemble methods. And ensemble just means it implements all of them and stitches them together in some meaningful way, in exactly the same way as automatic machine learning methods do that. And this is for decoding from movement. Think about a monkey that does that. We have electrodes in there, and we want to just have a good decoding of what the animal does. And the finding generalizes. You find it in different brain areas like hippocampus, somatosensory cortex. What we always find is that of the techniques that people know about, some of them are better than others. It's very hard to know which ones will be better than others. And by stitching them together, you do a little bit better. But it has two advantages. One advantage is that like you do better, which is great. The second advantage is that you save a lot of time because you just use all of them. You don't need to think which of them is best. The third advantage is that it avoids certain kinds of cheating. So if I try a machine learning algorithm on a data set and I use all the data, and we'll talk about it later, there's a chance for me to do what's called overfitting. I basically use the machine learning algorithm that worked well, and thereby I do better than I theoretically can do. Here, the alarm is going off again. Here you can see, here you can see for the encoding case. In this case, it turns out that it's a different method, XGBoost, that does really well there. Again, the ensemble method does better. And again, looking for hippocampus and somatosensory cortex, same finding. So you can basically produce simple machine learning techniques that combine the advantages of all kinds of other machine learning techniques, making things easier to run. I should have a little bit of an insert here about a recent study that we did with Danilo Bzdok's lab. So what we wanted to know is how much does it help to have complex machine learning systems? Like if linear regression is always tends to be enough, why are we going down that road? And it turns out, and that's what you see on the left-hand side, for a lot of machine learning data sets, on the x-axis, you always have more samples. And in different colors, you have differently complex machine learning systems. And what you see is that for the typical machine learning data set, for all data sets, it helps dramatically to have more data. And it's almost like accuracy linearly gets better with a log of sample size. Of course, there has to be some color, some convergence on the right-hand side. No, we can never have accuracies greater than 1. For the machine learning problems that people typically use, it helps an awful lot to have a clever learning algorithm. So for example, a convnet is what you see in blue, does much better on MNIST or fashion MNIST, which are two of these standard systems that people use, than say using a linear discriminant analysis. All of them, however, gain an awful lot from having more data. But the interesting thing is if we then apply these methods to fMRI or structural MRI data for a broad range of tasks. I can just refer you to the paper there. There, it doesn't seem to help all that much. And in fact, linear approaches work surprisingly well. Now, what's our intuition for that? So imagine if we had non-noisy data. A nonlinear classifier would do best. So what we have here, plus the positive data, maybe the disease data, minus the negative data, we'd have a nice nonlinear curve going through them. But if I then add noise to the data, it will mix the pluses and the minus, and it will, by doing so, make our decision boundary more and more linear. So as we add arbitrary amounts of noise, we will always, or almost always, converge into a linear classifier there. So let me now talk a little bit about like ways of doing machine learning wrong that are actually surprisingly common. There's cases where people ask the wrong question. There's wrong ways of assessing quality. There's wrong ways of comparing and wrong ways of managing the project. And I want everyone to be aware of like these issues. So the wrong question is the easiest. No, we have a real cultural problem. We have people that do great, amazing machine learning in computer science. We have people who do amazing work on the medical side. We have relatively few people that are cross-trained between them. So most people doing machine learning come from computer science, know relatively little about medicine, and they often ask medically irrelevant questions. And I include myself here. Now, it turns out that it's surprisingly difficult to come up with a scenario where it really helps if you know my mood state for driving an intervention. You better be really, really good at figuring out what my mood state is. So here's a very interesting mistake that is surprisingly common, as I will show very soon. In machine learning, we use this thing that's called cross-validation. So what that means is, say, we train on some of the data, and then we predict another part of the data. And if we're good at predicting that other part of the data, we will say, we expect that it now would also work in reality. Because, well, why is that? Let's go through that. So there's what I would call the correct way of doing cross-validation on the left-hand side. We take, let's say we have 5 subjects. Of course, we'll have more, like never use machine learning for n is smaller than 100 pretty much. But we take 4 of the subjects and we train our model on those 4 subjects, and then we make the predictions for the 5th subject. And then we will test how good our predictions are. The logic there is we're not looking at that one person. And the other part of the logic is we approximate the real clinical scenario where what we want to do is train our machine learning system on lots of subjects in a study, and then build a device, build a system that we can use for clinical practice. And so this was called subject-wise cross-validation. Now, subject-wise cross-validation is difficult because you will have very few samples. No? It's very expensive to recruit 100 subjects to do a proper machine learning study. And therefore, most people don't. They do something, or a lot of people do what's called record-wise cross-validation. How does that work? I now take the same 5 subjects and I divide it into 6 blocks, giving me 30 blocks. And then I predict each block based on the other 29 blocks. Why is that problematic? Well, if Konrad has some property, let's imagine Konrad has some disease, and Konrad also has a certain length of his nose, then because we have a small number of subjects, I can tell you exactly this is Konrad based on the feature of his nose length. And I can tell you, because I have the other 5 data points from Konrad, if he has the disease or not. So you can replace for record-wise cross-validation disease recognition with the identification of the person. And it turns out that for most real-world data sets, identifying the person is relatively easy. Take motor control. Like, people have their own rhythm of walking. They have their own idiosyncratic ways of behaving. And so it's relatively easy to know who's who. And if you can figure out who's who, then record-wise cross-validation gives you the wrong impression that you can diagnose the disease based on the data, which would never work outside of these 5 subjects. So let's first look at it if it works. So we did a systematic meta-study of the literature where we looked at 200 papers, followed a standardized paradigm, PRISM. And what we did is we looked at subject-wise versus record-wise cross-validation. Like subject-wise is correct, record-wise is wrong because it doesn't approximate the clinical use case. And what we find here is that, as we should expect, is that subject-wise gives you much worse classification errors. Well, because you're not cheating. But and there's a few versions of that we looked at. People use multiple folds where they divide the data into different numbers of subsets. We can look at how many different subjects they have. But in any case, for all of them, it produces a massive bias. Oh, no, hold on. This was like simulation works. And what we find is that, if people do this kind of cross-validation, it looks like they're doing much too good. So their classification error will look like it's extremely small. It gets slightly worse as they have more subjects. But the true error would be very bad and would only very slowly get better as you increase the number of subjects. So we did a thorough literature review there, looked at 368 records, removing duplicates, screened 200 of them, and basically read the full text of the articles to make sure how we could classify that. And here's what we see. It absolutely helps. So the average of, so the first thing is about half of the literature does it wrong. And they get better classification error. This is on the right-hand side, we have record-wise. On the left-hand side, we have subject-wise. Average classification error is 5% for the cheating record-wise papers, and it's 13% for the non-cheating subject-wise ones. So this is very worrying, and of course, it's highly significant. Let's see what we can say. Well, if this is cheating, okay, now we know that there's part of the literature that does things very badly. But the literature, we always live in this world where we believe that the literature is basically fine. So if that was the case, then the record-wise cheating papers should get cited much less than the papers that basically cheat and get themselves like a really good classification error. Turns out that there's almost no difference. And like we have 10.5 average citations for the subject-wise and 9 average for the record-wise. They're statistically indistinguishable. In other words, there's massive cheating going on. It doesn't do anything to the papers, but it does something to the infrastructure. Like we have all kinds of machine learning papers that get people really excited because, like, look here, they can diagnose this disease based on this kind of data. Isn't that super useful? Let's go. No, all the papers that do record-wise cross-validation have not provided any meaningful evidence that they would work in reality. And for every machine learning study that you see in a journal, you will basically, you will have seen so many of them in journals, and you have not seen them in clinical reality with very few exceptions. Why is that? Because as we see here, elementary statistical mistakes endemic in the literature. So what else could we have? Like there's another way of that really matters, which is how you compare to establish that your method works well. So what we often, and I should say this is a joint paper with Demasi and Recht. So people often report that how much variance they explained. And so you read a paper and it has 90% variance explained. And you're like, wow, that is pretty amazing. This must be basically, if it explains 80% or 90% of the variance, why are we even measuring things in clinical reality anymore? Because we can do everything with machine learning. Like the vast majority of the variance is explained. Well, let's have a bit of a look at that. So there's a lot of machine learning that predicts features based on phone use. No, and what we have here is we have two different data sets. We have the student life data set where we predict stress, and we have the friends and family data sets where we predict happiness and stress. Now, what's the right way of building that? You can say the classifier that I want to use to predict how Konrad feels should maybe be very different to the classifier we use to predict how Babak feels. Now, they're different people, they do things differently. And so it makes an awful lot of sense to make the predictions be specific to an individual person. So what we see here is in each of these data sets, we have the root mean squared error for the population, where we can say we take a classifier for everyone, and we see that in purple. And then we have on the x-axis, we have a root mean squared error of the prediction. And in yellow here, we then see how good we do if we have a predictor for each person. And what you see is every person I can predict much better than the average of the people. Why is that? Well, let's see why this is the case. Not like it's an interesting puzzle. And in a way, it makes sense. Not like Konrad, by having a specialized Konrad predictor, I should be doing better. And it makes a lot of sense to use such a specialized predictor. So let's see what we have here. We have the three data sets as on the previous page predicting stress, happiness, and stress for the two different data sets. On the y-axis now we have the root mean squared error. So we have the population base, which is the variance in the population, and we have the population model. And you can see the population base in the population model is a little bit worse, a little bit smaller. Basically, the model describes something that is real in the data set. That's why the population model, which is one model fitted to everyone, does better than just not having a model. But the models that we have do much better. And so in yellow, we see the personal variance and the variance residual after using the personal model. Now, what does that mean? In yellow, we basically see that the variance of Konrad is much smaller than the variance across the population. Well, why is that? Well, because like most people's stress level, it's kind of there's people that are usually stressed and people that are usually not stressed. So therefore, if I just assume that a person is close to their average stress level, I will have much lower variance than if I assume that they're at the population level. No, Konrad's a low stress kind of happy, lucky guy, like stress levels like 3 out of 10. And on bad days, it's 4, and on good days, it's 2, and some others, it sits at 7. And so what we have here is that the model that just says that everyone is sitting at their own baseline actually does much better than the population model. And what we see is that the personalized models, and this is the distribution across papers, personal models do basically, the distribution across people, personalized models basically don't do better than the personal baselines. So we introduce here the concept of a user lift, where you could say it's not success of your machine learning. And hold on, there's something that's really important to explain precisely here. The measure that people use R-squared uses the residuals when fitting a model. Basically, how much of the variance how much is the variance of my stress level minus the predicted one, and compares that with the population variance, where I take every person's every day and I look at what the variance is of that, which is of course much bigger. User lift is how much it gets better if you have the super trivial model, which is Konrad's stress level is Konrad's average stress model, and you ask how much better it gets if we now also have a machine learning model for the rest. No, like the thing is, this every person has a different baseline was in the previous literature counted as an advantage of a machine learning model. Whereas it's just a super obvious, trivial side effect of the fact that everyone has their own level of stress or their own level of mood. And user lift is basically how much does the machine learning model help relative to not having a machine learning model. The interesting thing is, in a lot of cases, it does worse. So having a machine learning model is worse than not actually having a machine learning model. So let's do some literature research there. We do emotion and stress. We select the first 200 papers. We have a bunch of inclusion-exclusion criteria. And that gave us about 20 papers in each group that did these things. So what you see here is the scaled prediction error. And we have the population baseline, we have the population models, personal baseline, and personal models for all those papers. What you see is that the personal models are only a tiny bit better than the personal baseline. So it's not actually all that helpful. Does machine learning even help? On the y-axis, you have the user lift. There are, out of these papers, there are 3 papers that are worse than not having any machine learning at all, and the remainder has a very small benefit. Keep in mind that it looks like everyone has like 80% quality in the model, an R-squared of 80%. Why do they all get an R-squared of 80%? Because predicting that your stress level is your average stress level just explains roughly 80% of the variance. But that makes machine learning useless. And so it's this wrong comparison. Like if it was true, then we don't need to ask anyone. Like at first you might think you don't need to ask people anymore because you're so good. But in reality, you're not so good. It's just that people's variance is small relative to population variance. Okay, cool. What else do we have? People often have wrong ways of managing. So if you're a clinician and listening to that, there is a way of avoiding all the bad things that could possibly happen. You get the data, apart from bad comparisons, which you also have to, which you need to fix. You get the data, you give only half of them to your machine learning collaborators. You lock the other half away. Never let them see it. Let them give you the algorithm and then test the performance on the parts that have not been seen. It's easy for machine learning systems to be overfit to real data. And I should also say, like, one of the big conceptual problems in machine learning is what's called leakage. Some people don't use cross-validating, but most people today use. There's lots of ways of validating things wrongly. For example, recruitment strategies or cross-validation errors by trainee who try the same algorithm on multiple times and improve the algorithm, but by doing so, they overfit the data. And I want to share as the last thing a spectacular failure of myself back then, which is why I'm so worried about machine learning techniques in medicine. So back in Chicago, we had run this cool stuff where we gave mobile phones to lots of patients who had Parkinson's disease, order 30. It was too small a study. I wasn't quite aware of that at that time. And they carried it for a few days and we collated all the data. And we were able to really predict well the UPDRS scores of them. And the hospital was blown away by it. They did a press release. This story, an app to track Parkinson's disease, came out in Time Out Chicago. And then we replicated the study and it went from an R-squared of 0.9 to 0. What had happened? I had a great postdoc who tried a few things. And I was strongly believing it should be possible. So he tried really hard. And of course, every time he tried things get better. And we weren't mindful back then of that possibility that you could be getting better through just trying many different machine learning algorithms. So,
Konrad, we actually have a question that came through
awesome.
Slido. So even if user lift is small or 0, isn't correctly identifying where a person is by itself useful? Does it mean we get no gain over baselines? Do we still not gain something even if average accuracy doesn't go up? For example, less variance in predictions?
Yeah, great question. So let's talk about common sense there. So if I would deal with patients who have potential mood issues, I will very much have, I as clinician would very much focus on their distribution. Like person X tends to have depressive symptoms, person Y doesn't. So every doctor in a way, every clinician will use a subject-specific baseline. And so machine learning uses the subject-specific baseline implicitly. It learns it, and learning just means it takes that average. And so it mixes kind of two things. It mixes a very simple strategy, which is reference things relative to the subject's previous distribution, which people do all the time. And it mixes that, and we use features from mobile phones to get better at that. So, but in a way, the things that's expensive and the things that make us excited about it is the idea that like mobile phone features could allow us to do better. And the same thing is everywhere in medicine. Like we use machine learning because it promises to make things better. If we don't have user lift, yes, it means that there's a difference across users. And yes, absolutely, if I would review the charts of someone on anything that's disease relevant, I would look at what's the value around which it tends to distribute. And people do that all the time. It's just that this is then not a success of machine learning, but it is the simple fact that things are very heavily correlated with with themselves over a long period of time. Now, let's say, let me give you an extreme case of a machine learning system that would be very wrong. Imagine we have people that have like slightly different baseline temperatures and very little variance around it. Okay, so both people measured body temperature on a daily basis. We're really good at predicting it, which is that it's always the same for that person. Such a system couldn't measure that I have fever now because fever is really rare and therefore doesn't contribute anything to the overall variance. No, so a machine learning system, if we attribute this to machine learning, would have great performance. Namely, it uses the fact that some people have higher versus lower body temperatures, and it would have zero user lift, but it would also be useless, no, because it doesn't tell me when I then actually have an issue. So, and if you have a predictor of mood, and the mood predictor will basically just say, look, this is Konrad. Konrad's mean is 7. I will say his mood is 7 every single day. Then it could never warn you that one day Konrad feels worse, which is exactly when it's clinically relevant. But this is a great question. Thank you. And let me briefly just wrap up the acknowledgement slide here. Of course, like this is all based in collaborations with various groups. And they did fantastic work there. And it's time for questions.
Yeah, so I do have one comment that came through. So I'm wondering what your feedback is on this. So this must be a joke. Censorship is the exact opposite of what we need in science. There were valid questions, one about ethics and ML, like the risk of wrong predictions or the abuse of ML deepfakes. Do you have any comments on that?
I'm not sure I fully understand the question.
I think the questioner is asking, they probably typed something in the Slido and their question is not approved yet. So they're assuming that is not going through. But the questions, Janitha is looking at the questions and is going to read them. So it's not, we're not censoring any questions.
Okay, now I understand where that's coming from, because I didn't think we were censoring any questions.
No, we're not censoring any. But Janitha is looking at them individually and then typing in your question and asking you.
Okay, fantastic. Cool. Can you reread the question then, please?
Let me just find it and I'll read it for you. in the meantime, while we look through all the questions, everyone, please use the Slido link that was in the invitation, or you can use this, what is being shown on the screen, the QR code, to go to Slido and type in your questions there, and we will relay them to Konrad. Okay, so while Janitha is digging up that questions and other people are typing in their questions, Konrad, thank you so much for this wonderful talk. Thank you for accepting our invitation and presenting for us. I really like your talk, and especially the part where you were covering the common mistakes and the analysis that you did on the literature. That was really interesting. Let me just.
Okay, so I found the questions. So the advances in ML are both fascinating and horrifying. How can we ensure scientific progress without having to fear super realistic deep fakes, videos, in times of people fearing fake news and so on? What should we as researchers do? What should society do? What is the role of politics?
Okay, this is a great question. It's slightly outside of what I was talking about. I don't think there needs to be much risk for the moment that people will successfully fake patient data. We are far from that at the moment. But more generally, yes, machine learning is used in all kinds of ethically great and ethically horrible ways at the moment. Ethically great way is not it helps us solve a lot of problems that have been relevant for us. It will, for example, help us probably bring down the number of traffic accidents, which is fantastic. But at the same time, yes, it can now start making images that look remarkably similar to the way people have images. There's a lot of fake reviews out there. There's a lot of fake images. There's whole ways of pushing our democracy in some way. What can we do about it? There are lots of ways of making these things better. There are ways of demanding that algorithms fulfill certain ethical standards, and there's just wonderful work. And there's a great book that I can highly recommend, which is by Roth, and Aaron Roth is one of the authors. It's called The Ethical Algorithm, and it tells us a lot about why we should worry about about ethics in algorithms. More generally, I think, yeah, we like a lot of good techniques. They can be good or bad, and we need to worry about that. And the general public needs to ask, what are the scenarios that they're willing to live with. For example, what if photos on Facebook have to be tied to your name? Well, it completely rules out all AIs if they demand proof that you're your person. At the same time, it basically doxes everyone, and everyone will know who everyone is. So we will need to manage this transition from a world where AI was rather dumb to a situation where AI can do certain things. But my talk in a way projected a different image. It said that a good part of the hype that we currently have in machine learning might not all be that justified, because many times there's wrong cross-validation. We have real problems with say comparisons, which make machine learning look much better than it really is. So I don't think machine learning is quite at that level where we can't distinguish it from humans yet. Nowhere close, in fact.
So the next question we have on the screen is, with Auto-ML, can you see which features are most relevant?
Yeah, with all machine learning techniques, you can in principle ask which features are most relevant. Most people who come from outside of machine learning really want to ask this question, which features are most relevant. The problem is it's almost always impossible. It's much easier to build an algorithm that works well than figure out why it works. So figuring out what the most important features are is often an ill-posed question, and you need really, really large data sets to know that.
And the next question is deep learning new electricity or new chemistry?
Okay, this is a great question, and I want to give my friend Ali Rahimi's answer to that, which is machine learning is the new alchemy. It works, but we don't really quite know why it works. And in that sense, it's different from both electricity and chemistry, which we understand really well.
And the next question is, you showed performance as a function of number samples, and results were not surprising. XGBoost coming on top. Have you done or are you aware if others have done analysis on performance as a function of distribution of labels or balance?
Yeah, I think we understand mathematically quite well how balance, say, matters. You know, like it just means that one class is very small, which effectively means that that the results will be wrong in an understandable way. I'm not sure if people have done that that meta-analysis. I believe in the paper with the RACT lab, there is some analysis on class balance. No, like class balance also allows weird, apparently correct answers. For example, if a disease only occurs in 5% of the population, if we are mindless of how we compare, we can get it 95% right by just assuming that, just predicting that no one has it. So consequently, it's really important to worry about label balance, and writing a meta-analysis, that would be very interesting.
I'm going to jump in. It's past 1 o'clock, and there have been quite a few questions. And thank you again, Konrad, for a wonderful talk and for answering all the questions. I think we need to wrap up as the time is approaching, or in fact, we're a little bit over time. So I'm going to thank you on behalf of our institute and everyone in the audience. I don't know, we still haven't figured out how to do online applause, but everyone please join me in thanking our speaker in a virtual form. Thank you.
Thanks for having me.
Bye.
All right, I ended the stream.